Authentication is hard, and passwords are not the best solution. We've seen this for decades now. The amount of cost and issues that come alongside using passwords as your main authentication solution is just not viable at all. Thankfully, we're starting to see the industry change this. We saw the revolution with YubiKeys, we're starting to see biometric auth, but most importantly, we're starting to see a really nice new standard called Passkeys. What are Passkeys? That's a great question, and I'll be honest, I don't have a great answer just yet. Thankfully, channel sponsor Clerk wrote an awesome article and decided that it would be a good idea to pay me to inform all of us about it. So yeah, this is a sponsored video from Clerk. That does not mean that the things we say about Passkeys are false in any way, simply that they wrote this information and they want me to share it with y'all, so let's do it. Anyways, Passkeys aren't just some new thing that nobody supports yet. There's a bunch of places that support them. We got Adobe, Amazon, iCloud, Bitwarden, Coinbase, Discourse, GitHub, Google, and a ton more. And I'm sure even more will be supporting it over time. It's not some weird new thing. This is a real option. What are Passkeys and how do they work? Let's dive in. Passkeys are a big step towards a passwordless future. Allowing users the ability to sign in with their device or biometric data, Passkeys provide a streamlined and convenient way of logging into supported services. And while convenient, they're also very secure thanks to the underlying tech that makes it possible: public key cryptography. Interested in learning more? Yes. So what are Passkeys? I have a vague idea. I'm assuming it's something similar to like how TUFA works with the like TUFA codes where it generates something based on the current timestamp plus the key that's saved. I'm guessing it's just that but automatic, but I could be wrong. Let's figure out how wrong I am. Passkeys are a method of signing into sites and services using cryptographically generated keys, which are often stored on physical devices like a hardware token or a modern smartphone. When a passkey is created for a user account, the device that is being registered for the passkey will generate two keys, a public key and a private key. Okay, so this is going to be more like SSH. In case people aren't familiar, I'm going to quickly sketch out how this works. We have this box, and this box does something specific. If you take a shape and you put it through this box, out comes a different shape. So if we put in the circle, then out comes this rhombus every time. Now imagine you can't see what's on the other side. We actually have a big block preventing you from seeing the other side. You can still see the box and how it does the transformation, but you can only see what came out. This is actually a really useful thing because it means I can prove that I'm me by generating a rhombus because I'm the only one that knows what's on the other side of the circle. And if you'll put through different shapes through this translator, obfuscator, whatever you want to call this part, usually this is doing some crazy math stuff in order to make it so the data gets transformed in a way where you can only go one direction reasonably. So if you have a public key, that's the thing that's on the outside here, the thing anyone can see but nobody can create because nobody has the other side. And then the private key, so to speak, is the thing that is hidden back here. Where things get much more interesting is what you can do with these things. Since we have this key that is some data that has been shared publicly, but you can only get this key if you have the private key too, or if you've shared it. You can't go from here to there. So I can't put a rhombus in on one side and put it through and expect to have a circle come out the other side because these transformations are one way. Usually the way they do it is some crazy like exponential math where they multiply the numeric value of this by an insane amount and then just take like the first 10 digits or so. And now you can't really do anything with that. Like you can't go backwards unless, as people are saying in chat already, unless you have a quantum computer. Oh, prime numbers. Yeah. Shout out prime. I don't fully understand the actual cryptographic means of doing these creations, but I generally understand the concept, and I don't think it's super important you guys understand the specific methods in the math either. Just the idea that when you have some algorithm like this, you have a private key that's a randomly generated thing. Through that, you can transform it into this piece of data that is fine to share. Anyone can have this key, and it doesn't matter. You're good to go. But what you can do with this that's really cool is you can use this to take a piece of data and encrypt it such that only the person on the other side can read it. So if I take something like I take the string hello world and you multiply this string by the rhombus or whatever you have as your like symbol. So hello world times rhombus, and this equals some crazy thing that is useless to you. If you were to encrypt this, the result would be some crazy string like a bunch of stuff that is meaningless to you. And if you have this public key, you can't divide by it because again, it's not actually multiplying, it's doing some crazy factorialization stuff. So you can't divide and get this back. It's using the prime factors that you need the original numbers for in order to translate this back. So now, once you've done this transformation, when you take some data that you want to protect, and then you want to lock it in a way only someone else can unlock it, you would combine the data you want to protect with that person's public key. And now the only way they can prove that it's them and read the stuff that you sent like this is to use their private key to unfurl it. So in this case, when we're trying to authenticate, let's say we have a service. For the sake of the sponsorship, we'll call this Clerk. So I want to go into Clerk. So I'm a user. So I will go to Clerk and say, hey, let me in. I'm Theo. And Clerk says, oh, that's Theo. I already have this rhombus for Theo. I already know this public key, but I want to make sure this is actually Theo. So I'm going to respond with something. What we're going to respond with is some unique string, like this is a test to see if it's actually you. Obviously, this text would have to be unique every time you send it back. So here we're going to send this back, but remember, it's been transformed by the rhombus or whatever your public key in this case is. So we're not actually sending back this text. We're sending back a whole bunch of gibberish again, and then use the private key to decrypt it and then send it back to let Clerk know, hey, by the way, I am actually me. Here's proof I was able to unfurl the message that you locked. If you want a simpler way of thinking of this and you don't want to care about any of these details, which honestly, I understand, I kind of fall in that boat. Public key equals only locks. A public key can lock something, but it can't unlock the thing. Private key can unlock. So that's the core concept here. A public key is something that can only be used to lock some data. And the private key is something that you securely store yourself, either by remembering it with a password or ideally saving it as a big encrypted thing. If you use SSH with Git, you already have a private key that is used locally to verify things and a public key that is used on the other side so that they know they're actually you. I like the analogy that Angelo just dropped in chat. Generally speaking, public key is username, private key is password. That's a good enough way to understand this. Another great way to summarize this is the mixing paint metaphor. First, Alice and Bob agree on a common color to use as their base. Then they each choose a secret color paint to mix into it. The mixtures can be shared without revealing the colors or the quantity added to anyone who may obtain a sample. So Alice and Bob mix the same proportion of their secret color with the received color to both end up with the same color. Yep. So the only way you can take this original color and then get to the color that you want to have is if you know the missing part. Hopefully that helps summarize what the public and private key are and why they are important. Back to it. So how is this related to passkeys? Well, they're using public and private keys. The passkey itself is a private key on your machine, and you give a public key to whatever service that you want to be able to sign into. Let's see how it actually works from there, though. These keys are then used to securely sign into the service where the passkey is registered. When the user tries to sign in using a passkey, the client will request a challenge from the server. This is similar to what I was showing in the diagram before, where they will send something that you can only use if you have the private key. To go to the color analogy, because I actually do like that, even though it's a bit hard to wrap your head around initially. Let's say I have the color yellow and the service has the color red. When we combine them, it becomes orange. The thing the server saves isn't the yellow or the red. The red is what Clerk has. The yellow is what I have. Orange is what the server saves, because the server knows when I combine my color with the server's color, the result is orange. So now, whenever I want to verify that I'm me, they send me red, and then I combine it with yellow, and then I can send them back orange to prove, hey, look, see, this has to be me. I'm the only one who knows what color should come when you send me this red. So that's roughly how it works. Obviously, the encryption lets you do more to make sure people can't fake it, and they don't know what color the other one has just from the result. But the mixing of the colors makes it harder to know what exact proportions go in. Kind of works like that, but on a much higher mathematical level. So as I said here, the client then signs this challenge with its private key and then sends it to the server. Once received, the server checks that the signature is valid using the public key. Okay, so it's actually a little bit different. Instead of trying to decrypt the message that the server sends, it's the opposite. One other thing you can do when you have a private key is you can verify that you are somebody. So if I was to take this message and I was to multiply that by my private key, it's not going to lock it. And I saw people asking earlier, can you lock a message with a private key? Kind of. But what you actually end up doing usually is very different. Let's say I want to prove it's me, and it's me right now. Hey, I'm Theo, and it's July 5th, 2024. If I want to prove that this is a message I actually wrote, I can go through my private key and multiply it, and it's almost like stamping the message to say, hey, here's a stamp attached that proves it is me. And you can verify that because it has the signature from my public key. And you can look at the public key that I've distributed already. You can look at the message and see a signature that only could exist if those two pieces of data are lined up. This is how a lot of RSA and basic public key encryption stuff works. I can do an example. I was going to run locally, but I'm lazy and I don't want to do anything SSH locally when I'm streaming because that might leak a key. I don't feel like dealing with that. So the way this would actually work usually is you take some message like, hello, this is a test, and then you generate a hash, like a checksum of that message. So that will be a short string that is generated by using that specific function on this specific message. Then when you have that hash, you can sign it using your SSH key. And the result's going to be something that looks like this. This is the unique combination of the private key and the message, and it is linked to the actual message you sent because it matches the hash of that message. So now you can use SSH to verify that this signature is actually coming from the person who owns that private key. And then when you run the SSH verification, it will tell you that the key lines up with the public key that you had already saved. So that's the basics. It's mathematically complex. I'm not pretending it's not, but the core concept is you can use a private key to verify who you are, either by unlocking something that was locked with a public key or by signing something with a signature that can only be verified if you have that private key. And then externally, people can confirm it's actually you by using the public key. So those are the two concepts. Again, it's like the public key is the username, the private key is the password. The only way I could make a post on my account is if I have the password, but others can confirm it was me on my account because they see the username that made the post. It's effectively that, but signed mathematically. So the way that this is working here is the client is then sending the server something that we signed with one of those signatures that says, hey, confirming this is us, and then they can make sure that that signature matches based on the public key that they've already gotten saved. Provided the signature is valid, the user is then signed into the service without having to enter any information manually. So here's the back and forth. Actually, it looks quite similar to what I was drawing here. So the user hits the server sends something back to you, which your computer sees, and then it creates a signature for it. It sends that signed message back to the server. The server then verifies it against the key that it has saved. And then once it's confirmed all that, goes back to the user, you're now let in. The use of Passkeys creates a passwordless experience that is both convenient and secure for the user signing into the service. I do want to emphasize how bad passwords are. There's a great story where Microsoft talked about how much they lose money from passwords. Finally found the source on this. That was annoying to find. From estimates from these various studies that were done, 25 to 40% of all help desk calls are due to password problems and resets. And there was a single month in 2017 where Microsoft had to reset 686,000 passwords for employees, which cost them $12 million in support. That's insane. The amount of money it costs to deal with passwords as a business, especially considering how insecure they are, is kind of insane. Like, holy shit. Passwords suck. It's not like, oh, passwords are silly. It's like, oh, passwords are very dangerous. And there's like a $1 trillion industry. Like straight up trillions of dollars are spent on people hacking accounts with passwords. There are constant breaches like all of the time. Even when I was researching this, I found even more. The war on passwords enters a chaotic new phase from Wired. Yeah, the transition from traditional logins is getting messy. And a lot of this is just because of the level of breaches that are going on. Like there are so many attacks on passwords. There are so many lists of passwords that are just public now. Like, have I been pwned? Which everyone should have checked, ideally a few times by now. You put in your email address and it tells you how many breaches they know of that your email and possibly even password have been included in. 10 years of breaches. And this was in 2021, so it's gotten even worse since. Yeah, the just sheer number of breaches, like over 164 million breached accounts on LinkedIn. Just so much stuff gets hacked, and a lot of that is passwords. So because passwords are fundamentally insecure technology, we have to worry about these things constantly. Anyways, hopefully that makes the case why you shouldn't be using passwords for your things if you can avoid it. I tend to lean towards just doing OAuth where you can and then using TUFA where you can't. Also, don't use SMS TUFA. I don't even want to start that rant today, but SMS is not a good way to authenticate anything. So how does the public key crypto work? To understand the magic behind passkeys, it's worth understanding how public key cryptography works. Public key cryptography works by using a pair of keys in order to securely store, sign, or transmit data. Private key can be used to encrypt or decrypt data, as well as generate a signature based on that data. The private key should always be stored securely, since anyone who has the private key can also sign and decrypt data. Again, very important, that private key, you do not want anyone to have access to but yourself. As long as it's just you that has access, everything's good. But the moment that changes, things can fall apart. Usually the best strategy is to actually encrypt your private key with something else. As funny as it sounds, we have like these 15 layers of encryption and obfuscation now. It is actually really important to have your SSH key encrypted in a way that you can only access it with something like a password. And it sounds terrifying, but the value here is that you have that one password that is only ever entered offline on your system. And then the thing that is sent out, the thing that leaves your computer, isn't the password that you used for that SSH key. It's not the SSH key either. It's the things that you're signing with it so people know that you are actually you. That's why this pattern is so powerful. Also, as Angela points out here, you can also protect a security key with a physical security key. So if you want to make sure your private key, like your SSH key, can only be accessed by you, you can actually sign it with a YubiKey. So you can only open it if you have a physical YubiKey attached to your computer. Anyways, the public key can only be used to encrypt data or to validate a signature from the private key. Again, private keys can only lock and verify. They can't unlock things. The public key can be distributed without risk, as its primary utility is to secure data before sending it to a destination that has the private key. Because the system uses two different keys, it's also referred to as asymmetric cryptography. Yep, this is the standard for almost all crypto nowadays. A practical use of public key crypto. While passkeys are relatively new, public key crypto has been around since the 1970s, and it has a wide number of applications as well as use cases. One such application that demonstrates these concepts well is end-to-end encrypted messaging. Let's say Ava and Brent use a secure chat app to communicate regularly. They each have a set of public and private keys. When they first connected, Ava would have sent her public key to Brent, and Brent would have sent his to Ava. When Ava sends a message to Brent, her device encrypts the message using Brent's public key, and the encrypted data is transmitted over the internet to Brent. And this is the important bit. Because that message is encrypted, it can only be opened if you have that private key. So it doesn't matter if your connection is encrypted, if you're on a VPN, if you're on SSH or not, because anyone could sniff that message and see what you sent, and they can't do anything with it because it's just that nonsense string until you use the private key to decrypt it. When Brent receives the message, his device would use his private key to decrypt it before displaying it. Now let's say Charlotte tries to intercept the messages that Ava is sending to Brent. Because the messages are encrypted and Charlotte does not have Brent's private key, the data being received is unreadable. Yep. So if somebody else tries to steal that message along the way without the key, they can't read it. Nice and simple. Even though this example uses a chat application to demonstrate how public and private keys work together, the same can be applied to the login process for passkeys. So if I send the... Did they screw that up? Where it should have been, I send them the public key and I keep the private key, right? I think they just screwed up what is what there. Get that fixed, Jacob. I see you in chat. So how are passkeys more secure than a username and a password? Well, there's a couple of reasons why. I already started touching on those. Let's see what the article has to say. First one is convenience, which might sound crazy because it's like, well, I have to keep track of that private key. That sounds way worse. Well, usually it's not because we have good UX around it, especially something like the new passkey standard that we're here to talk about. There's often an indirect relationship between how secure something is and how convenient it is. Passkeys, however, have the benefit of being convenient for users to take advantage of by providing a very streamlined experience to signing into a service. People tend to gravitate towards solutions that are easier to use. Combining the high security of public key crypto with the simplicity of just signing in by tapping a button, users of passkeys get the best of both worlds. This also helps solve the reuse problem, which is massive. Again, if your password is being used in 4 different places and one of them gets breached, all of your things are compromised now. And this is hilariously common. The amount of accounts I used to get when I was a kid just trying to get a cheap Minecraft account that I got because something else was breached and they used the same email and password on multiple services, it's insane. Let's see some ones in chat if you use the same password for more than one thing. Be honest, y'all. Ones in chat if you reuse passwords, 2 if you actually don't. Be honest, y'all. I'm expecting a lot of ones. Even low level is reusing passwords in here. I need y'all to understand how screwed we are as a society. There's way too few 2s and way too many 1s. Not anymore. Damn right, Gabriel. None of my staff are reusing passwords. Not allowed. Bait, don't disclose. Good point. You have a password that you've used for 15 years. That hurts me so deeply. That hurts me so deeply. Oh, God. Ow. You trust Google with auto-completing. Oh no, oh no, oh no. It's got the Google Chrome's passwords are a little less scary now, but before they weren't even like encrypted. They were just a text file that anything could sniff. So it's better than it was, but please use a password manager. Like KeePass is fine. I'm a 1Password guy, but you got plenty of options nowadays. Please use a password manager. Then you have 1Password, but it also has a private key that is used to encrypt your vault, which has all of your text which has all your passwords in it. So without your password plus the key, you can't access any of your data. So this is the right way to do things because of being set up properly. And it has passkey support. So you can store the passkey in 1Pass instead of on your computer. And now it will auto sign in for you with the Chrome extension. It's so nice. Please use something like that if you can. Don't reuse passwords. As I said here, with Passkeys, every service automatically gets a unique key pair. This means that if one service does lose control of its secrets, any other accounts you have that use Passkeys are still secure, eliminating the work needed to cycle your passwords in the event of a breach. On top of that, the thing that the server has isn't data that's useful anyways. When a server has a public key, you can't do anything with it. It's already public. It's like if a service got exploited and now they have everyone's usernames, who cares? They're just usernames. The fact that you're not giving them a password solves a lot of these problems by itself. Credential strength. One strategy for hacking an account is repeatedly guessing a password until the correct one is discovered. This is known as brute forcing, and password length is often the biggest determining factor on how realistic it is to brute force a password. The longer the password, the less chance it can be guessed. It's not just longer, by the way. A lot of these brute forcing attempts aren't just trying random characters, they're usually dictionary attacks. And as unintuitive as it might sound, you can work around that too. One of the things I highly recommend, I think there's an XKCD about this. People like to think that these really randomized passwords are good, but when you have common substitutions and punctuation and all these types of things, you're just making it harder to memorize. But if you're brute forcing that, it's going to be guessed relatively quickly still. And then you're going to struggle to remember it too. Whose passwords in chat look like this? Let's see some ones in chat if your password looks like this type of nonsense where you're replacing letters with numbers and shit. Ones in chat for you numbers instead of letters people. I feel better that there's a lot fewer of y'all doing that. That gives me some hope. That gives me a bit of hope. Absolutely never. Okay, cool. A passphrase is greater than complex password. Spoiling it. You don't know your passwords. Good answer. I don't know my passwords either. Okay, I know one of them, but only one of them. So the best way if you're actually writing a password, this is a good thing to use for your 1Password if you're using a service like that. Random words. So if you put like an underscore or a dash between one or two of these, now that you have 4 random common words, the amount of time it's going to take to guess that, if you're guessing without using a dictionary and you're just guessing letters, is insane. This is why dictionary attacks are now the norm, because it's really hard to beat this out. But even then, like 4 unique words without the knowledge that those 4 unique words are being used. Because the only way you could reasonably brute force is if you know if the person's only using dictionary words and you have the same dictionary they used. But if you could use a word that's not a dictionary, like a name or a brand or a proper noun or something that you can memorize, like I found this by Google searching correct horse battery staple, because it's very memorable. And if you have something that's memorable that is also unique, like a true, proper, unique sentence type thing, you're going to be very safe. And as crazy as it seems, correct horse battery staple is actually a much better password than whatever the hell that is. Yeah, as long as you separate, people are saying separate by random characters. I agree. If you separate that by random characters, you're very, very safe. Hey, don't share my password. Don't share my password in chat. Anyways, a 16 character or byte password is good, but a passkey's 100 to 1400 bytes, which is significantly better. Also, built-in multi-factor authentication. MFA, if you don't know, is checking in multiple ways that somebody is actually them. The most common one is I sign in with my username and password, and then Google or someone says, hey, are you actually you? We're going to text you something to confirm that you're actually you. And then you get the text, you get a little code, and then you enter the code, and now they know it's you. It's multi-factor because the password was 1 factor, and that code you entered is another factor. 2-factor means there are at least 2 things needed to verify that you are you. I do a thing that many consider controversial. I store my 2FA codes, as in like the application 2-factor stuff that will generate a code for you on the fly. I store those inside of 1Password, which might sound terrible because now, oh, you only need the 1Password and then it's going to fill all the data in for you. You've just ruined 2FA. No, you haven't, because you can only get in my 1Password if you have the key for my 1Password and the password for it. Without those 2 things, you can't get into my 1Password. So it's still 2-factor. I just cached one of those factors on my machine. That said, it's super important to have something like that. So just 1 string leaking isn't enough to ruin your life, especially if it's a short string. Especially now that we're getting in the days where like supposedly there's AI that can figure out what you typed based on the sound. That shit's terrifying. So having just 1 thing be enough to exploit you, that shit don't work anymore. You need at least 2 things locking your accounts if you want those things to be secure. And things like passkeys make that much easier. As they say, some common factors used are things that you know, something you have, or something that you specifically are. So biometrics would be a TUFA method or a multi-factor authentication method. If I can scan my eyes and enter a password, there's two things. That makes it exponentially harder to get into my account. For instance, if you sign into a service with a username and password, those are considered a single factor since you know both of those pieces of data, and one of them is also often public. Adding an authenticator app or a hardware token adds an additional factor since it utilizes something that you have. With Passkeys, MFA is built in. The device, along with the public or private key pair that it's generating, is one factor, and since biometrics data is often used to unlock the device, that's a second factor. Yep, since the Passkeys on my machine, you can only get to it via something like biometric auth. That's now locked away, and then that's used other places. I will say it's a little sketchy because once you've done the biometric auth, you're now in the machine and you have access to everything in the machine. But that falls into the same thing the 1Password example I gave earlier did, so we're going to justify it. Eliminate phishing attempts. Oh boy, this is a really fun one too. Since there's a public key, often there will even be a unique public key to that specific service. If another service pretends to be that first service, they can't really fake that. The same way if you go to a site with HTTPS and then you have your DNS sniffed and somebody's trying to redirect you somewhere else, the OpenSSL key that you save when you go to the site will confirm, hey, you're going to a site that isn't the one you think it is, by the way, just so you know. Oh, apparently Passkeys ask for biometrics every time they're used. That makes sense, especially on Mac because they have the Secure Enclave, which is a special chip that you can only get into with biometrics. So that makes more sense. But again, phishing means sending somebody a page that looks like another service, but isn't. So if I have my public key in Google, and then I go to fake Google and I sign in, they're not getting any of the data that they would need to sign into my Google account. They're just getting the signature response to whatever request they made to me there. So it's effectively impossible for me to sign in with some data to Google and have them get into another account. It's significantly better. Yeah, the ARM trust zone is insane. Absolutely. That's the fact that there are now things in your processor that are secured, so you have data that's only accessible under specific conditions, makes these types of things significantly safer. And most ARM-based processors have this now, which is dope. It's a thing that Windows is still catching up on because x86, despite having far too much support for far too much shit, didn't do this. And yes, shout out Apple for normalizing these things. You can absolutely beat Google. You know what? I'm gonna take a minute to bitch about Google because I'm actually quite annoyed. I have a very good TUFA setup going with 1Password. I have a lot of Google accounts because I run multiple companies and I have different Google accounts for each one. Google's multi-factor authentication requires that it notifies the app by default, even though I have a TUFA code app thing set up. So even though I have all the data I need to sign in, when I try to sign into Google, it will then send to my phone a confirmation, even though I might not even have my phone in the same room. I just want to use the key that I have in my 1Password, but it won't let me until I manually click like 3 additional buttons. And there's no way to change the default on Google. They do not let you do it. I have been complaining about this for forever. They do not let you do it. It's obnoxious. Anyways, if you have multiple options for your authentication methods, let the user pick which one. I'm okay with mandating 2-factor authentication, but let them pick which factors they want to use. And if they can use multiple, let them pick which one's the default, because that's what Google got really wrong here. Google has everything right except for that. I can't remove the phone off because it breaks other things like the verification of my YouTube channel. So I can't just do that. Trust me, I am more experienced in saving a fucking Google account than anybody in this chat. There is no way to change the default without putting my account at risk and multiple people's livelihoods. Please, I rarely appeal to just trust me, bro. Just fucking trust me, bro. Google does not make it viable to pick a better default. They do not let you do it, period. So as the article says, if you are being phished with a password thing, you can get fucked. For example, a user might receive an email that appears to be from Amazon stating that they're going to place an order that was never approved and tell them they can manage it using the link embedded below. You see that big fake check orders button on this fake email, you click it, the domain might be something that looks like Amazon.com, like Amazon.com. You don't even notice, and now you're signing into something and you're just handing them credentials that you don't intend to give them. Really sketchy, really problematic. Got to be careful with these things. Since that domain looks close, you end up blindly giving them the credentials. Yep. You don't click on email links almost ever. Type them out yourself. Since the passkey is generated on a device and that passkey is specific to the domain for which it was created, this removes phishing as an attack vector entirely. Again, they can't possibly get you to sign a request for Google. They can only get you to sign a request for their fake domain, like everyone's favorite Googie Analytics. So you're safe. The password only works on that site. That's the way to think about it. Instead of you have a password that can be used multiple places, every site has its own generated password saved on your computer. Because of that, things can't get compromised the same way. These attack vectors are just gone. It's a really, really nice win. Yeah, this also includes domain names that include non-standard characters that appear to look the same. Important detail. Google and Googie are different. So if you go to both and you even sign in properly on both, those are now two different passwords that are auto-generated through the Passkey system, which is really nice. And of course, Clerk supports Passkeys. That's why they wrote this article. And that's why they're sponsoring me to talk about it, because this is not an easy thing to set up yourself, and Clerk just makes it work automatically. Passkeys are officially supported authentication method for services secured with Clerk. You can enable them just like you would any other login method for your users. You just go to your settings and now you can enable Passkeys. Super nice. Once enabled, your users can add Passkeys through their user profile. Yep. And then once you signed in, they presented with that option when they're doing the sign in. Super, super easy. And I cannot think about how I would be setting this up otherwise, because these types of things aren't fun to do. I love Passkeys. I'm going to start using them much more now that I understand the core of it, that it's just basic public key signing and saving it in your secure enclave. That all makes sense to me. I'm feeling great about this. We got a handy demo from Gabriel. We got to try this quick. So what is a passkey? It's a new way to sign in. Yep, cool. Let's try it. Sign in with a passkey. Oh no. Anyone can see this right now. You can scan the QR code with the device that has the passkey that I want to use for the site, or I can use this as a USB security key instead. What I'm going to do, register passkey. Here we go. See that? The passkey is now using the standard browser API, and it will save that in my 1Password. In this case, my ping 1Password. So now that is saved in 1Pass, and now I can use this passkey on any of my devices because it's not the device saving it, it's 1Pass. This is a different place to securely store it, but you have options because it's a standard. And that's what's really cool about this. This isn't just like, oh, Apple's trying to take over authentication. This is a new standard for doing auth well and safely. Let me know what you guys think, and please, please, stop reusing your passwords. Peace.